This conference will now be recorded.
Welcome everyone. So today we'll have a presentation by Ariel Hendel. Ariel Hendel is a distinguished engineer. He basically started at so his education started as in Technion Haifa, where he got his master's electrical engineering from Polytechnic University. Ariel reached a distinguished engineer role at Sun Microsystems and Broadcom Corporation, both while developing networking and semiconductor products. At Meta, uh, when it was Facebook, Ariel was an infrastructure technologist for networking. And Ariel went on co-founding two jump starts in 2020. One is El Fabrica Corporation. The second one is Scala Computing in late 2021. Since 2008, Ariel industry work and academic collaboration have been around data center network and guiding silicon innovation to maximize large-scale data center efficiencies. On a personal note, uh, I had the honor to have Ariel as my mentor, and he taught me pretty much everything about PTP and Meta, and I'm very grateful for all the help and everything he provided to me. And today's talk will be basically about the simulation aspect that is necessary, and I mean with a lot of emphasis from Ariel's perspective when it comes to PTP. So with no further ado, Ariel, the floor is yours.
Thank you very much, Ahmad. It's great to be here. The credits are first for the title. I borrowed that with permission from Majid Ansari at Juniper, who uses the word validation. And you'll see in my talk, I'm going to try to double click into validation and argue that would mean simulation in our case. I think it's a great phrase. On the credit to Ahmad, because by the time we gave PTP a push at Meta, Facebook, kind of 2020, early 2020, it was in a completely different shape, and he completely shepherded that both on the internal products as well as the standardization. I had to catch up because I've been working remote from 3 different continents, 3 different states, and everything else during the pandemic. So I caught up with 2 years worth of work that the team did, Ahmad and the lad and a few other people. I think it's great work and it's very useful work. By caught up, I mean that I was binge watching the OCP YouTube videos as if it were a Netflix series. And I was trying to do that at 1.75x speed to save some time. Except for Ahmad. Ahmad, I have to put him at 0.75 speed to keep up with his rate. It's best if you stop me. Feel free to stop me anytime. There's no need to wait until the end. If there is a contextual question you have, feel free to stop me and ask the question. The other thing is they have a very dry sense of humor, and if you're all in mute, I'll never know if it's working or not because I'm gonna think that I hear silence, which means that my jokes fell flat. So feel free to unmute if you're not multitasking at home. So yeah, on that spirit, I have a kind of humorous version of my bio to make it not too dry and more humorous. I've been oscillating my entire career between systems and semiconductors with the belief that the guys on the other side are having more fun and there is more innovation, so constantly going back and forth. And I made distinguished engineer at 5 different Delaware companies: Sun Microsystems, Broadcom. Those two got acquired. Then Broadcom was acquired by Avago. It's now called Broadcom Inc. Then at Fabrica and Scala, both of them are startups that I hope that they eventually get acquired. That would be awesome. I was never at the E at Facebook because Facebook doesn't have the E's, and I mean doesn't have the D title. There are lots of people that are very distinguished at Facebook. So I've been D for so many companies that my joke is that the HR rep asked me to write the JD for the position. So that's my kind of recent career working for all these Delaware companies. Any questions? Moving on. So Scala Computing has a very singular model. What we're trying to do is simulate an entire data center in the cloud. So we can take an entire data center of the scale of something that Facebook would build and run it in a different cloud because Facebook does not sell VM capacity. So you can go to a different cloud vendor and can simulate that network or any other operator's network. Our business model is try to be a vertical SaaS business model, so you don't have to invest capex in building your own simulator infrastructure, and it comes pre-bundled with all the models, the tooling, and everything else. And that comes from my career, which started as a design verification engineer for Silicon. And I know from my personal experience that I love running simulations, but I hate building simulators. So this enables you to say, I want to be productive on my first day. Give me something that already works. My youngest son was a fan of our roller coaster tycoon game. You may be familiar from the Windows era, brilliant game, and it essentially simulates an amusement park. And it was done so well that you get an understanding of what the hell is going on. Like you can mouse over a person and see what the person is thinking. So you can have arbitrary, you feel like you're God. You say, we're going to increase the prices of the hot dogs and see what it does to attendance and stuff like that. That's a brilliant game. And I put as a note, as a footnote, that the guy that wrote it over the course of 2 years wrote it mostly in x86 assembly. Only the first year, they were already selling $20 million worth of revenue. So yeah, so that taught me that simulations are a great tool. But that son is a data scientist now doing his master's in analytics. So obviously it molded a little bit the way he thinks about things. The way we approach a data center, it's not a game, but it is a game. And what we do is we superimpose distributed application workloads on top of a data center network model at scale. If you wish to run at scale, you can do subscale experiments. The fun part of all the employers I work with, or most of them, is that we were always developing the tools that we use to develop the next tool. Just like software people design a compiler and compile it with the older compiler to have a new compiler. At Sun, we're doing workstations that were used to design the next generation workstations. At Broadcom and Intel, we're doing processors that used to design the next generation processors. At Scala, we're doing simulations that run in one data center so we can build another data center even better for the next generation. And that's cool. There are few industries that have that kind of recursive effect. If you're in the car industry, a car doesn't help you build another car. So that's just an aside. Scala came already once to OCP recently. We were here on May 10th, and we had a joint presentation done with Keysight, done by Jay Vargas and Dan, which was a very cool talk because we tackled the hard problem of how do you know that your simulation matches real life. And if you remember Keysight and Ixia, when I started back in Long Island, New York, the gold standard for instrumentation was always Hewlett Packard and then Agilent. I'll try, whenever I go to the lab to get HP instruments, I admire them. When my company didn't have enough money to buy one, I would get a loaner for a month from the sales rep. And I always aspired to use that. So we partnered with them to do one experiment where they took the part of the instrumentation on the hardware and we took the simulation. So that was very nice. And they run the emulation on real Linux x86 boxes. So it has the entire protocol stack, a real lake, and a real x86 server. So that is a real endpoint in a real network. And the simulation runs on distributed in S3 over MPI, so we can scale, and we host at AWS. Here's a link for the YouTube video for that talk. And there is an old line by Yogi Berra that says that you should go to your friends' funerals, otherwise they're not going to come to yours. So I'm reusing that line saying, unless you watch my video, I will not watch yours. How open is the platform? When you go to a data center, it turns out that the interoperability between competitors, because every data center is heterogeneous, happens mostly at the Ethernet links or on any other link that you have. So we mimic that model. At the Ethernet links, we're interoperable. So we're fully open, which means that we have stable published interfaces that people can design to. Having said that, we preserve the ability of the contributors to not to disclose the behavior of the internal models, just at the interfaces. We create a consortium to manage the evolution of the interfaces. The consortium is free, open to any Vodafone member that want to come and contribute. And it defines also the workflow, pretty much following the models that the semiconductor industry uses for sharing data sheets. If you go to Mellanox, to Intel, to Broadcom, and say, give me a data sheet, they're going to ask you, who are you? And if you're a potential customer, say, oh, here it is. Here, the beauty is that you can say, hey, give me a theory of operations. Oh, and we have a model for a simulation for that device. And you can say, yes, here it is. And you can share with all the potential customers or partners your models, just like you do documentation. There is a subtlety in this model. In OCP, I keep hearing repeating the mantra that everything has to be open source. Let's be careful. The silicon IP is not open source. The hardware is, the boards is, and some of the firmware, but the IP that is inside an x86 processor or inside an NVIDIA GPU or inside a Broadcom NIC, nobody's asking those vendors to open that and publish the RTL because that is their business. So that's exactly what we mimic. Openness to the degree that you can, which is hardware design, without compromising your IP. So it's slightly different than the traditional open source model that you'll find in the Linux community. So if I had to draw these interfaces I just showed, starting from an endpoint, I just drew 3 servers that are endpoints where you have an application talking to a network stack, talking to a network interfaces. The interoperability interfaces that we publish are essentially APIs, an application writing to a sockets layer or to an RDMA Rocky layer, where what you see of those APIs are messages. Then you have a network stack, which is another standalone model, connects over another API to a network interface. And that mimics more or less the semantics of load store and PCI. And then at the end of the day, the ultimate interoperability interface is a wire protocol over Ethernet. There is nothing more interoperable than that. And the NIC to switch fabric interface is just that. And then I have a typical example of a two-stage clause constructed out of Ethernet interfaces. Any questions so far? Am I doing okay? Are you hearing me?
Yeah, all good.
Okay, awesome. I thought for a second I was feeling I was talking to open air. So why are we here specifically at OCP tag? We think that we can help. And the first thing that we run into, and Ahmad knows this, is that you go to somebody and you say, hey, you don't need a GPS per server. You can deploy over a packet switch network time with very good precision. You're going to face some skepticism from people, and some of them are just random people, and some of them are decision makers. That skepticism in general is not organizational, it's personal. It's because that person came from a different company and he still has some egg on his face from an attempt to use a PTP for a different vertical. And it takes time until technology matures, and that person had a bad experience. Or maybe that person is biased by experience. Maybe that person is biased because he doesn't like the proponent. In many cases, if Steve Jobs comes up with an idea, the whole world says it's great. If Elon Musk comes with an idea, it's great. But all of a sudden, I don't know, my wife comes up with an idea of deploying a PTP in a data center, I'm going to say, who the hell are you? And it will not be treated with the same degree of seriousness. So I cannot fix humans. It doesn't matter how many unconscious bias sessions I do. I cannot fix humans. But what I can do is I can give you a simulation so the facts can speak. I can give you a URL saying, here's a model for the entire data center. If you're a skeptic, go ahead and break it. Here's the URL. You don't even have to code because everything is GUI driven. I'll give you a funny experiment. So our idea is to say what you're undertaking is hard enough. You're going to run the skeptics. Every big organization has camps of people that believe in one technology or another. So I can help you overcome skepticism by removing the excuses, saying, here's the simulation, have at it. There are some hard questions that we face every time we say, hey, can simulate something complex like a data center. And the one I already spoke about is how do you know it matches real life? And I told you the answer. We partnered with the king of the test equipment, which is Ixia Keysight, and we showed for a TCP workload, which is really hard, that we can get it within 1% match for a reasonable scale type of topology. We have every intent to repeat that with TCP. And we have at least 2 partners where we can repeat that exercise, and it would be very, very cool to do that. The other question we face is, okay, what's the workload? Are you running the real workload? The application and the protocol stack are going to run in real life? Not yet. For the applications we're running at the moment, we create written in C++ a synthetic application, which is like the equivalent of a micro benchmark that mimics our best understanding of the application. So we can focus on the network side of that application. The technology has means for executing binaries, and we're planning to do that next. We think that PTP is the perfect technology to do that because number one, PTP4L is the stack and the workload when you think about it, because there is no data movement per se coming from the application. Time is a service. So the stack is very separable from the application. In other cases, it's not the case. If you're running disaggregated storage, if you're running query, if you're running ML traffic, you cannot say I'm going to stay at the protocol stack and TCP level. You have to layer an application that has its own communication patterns on top of that for fidelity to be valid. PTP is beautiful because if I can distribute time with a given precision, I don't care who's consuming it. It's a service. The other reason that this is a very nice exercise for PTP is that it has a very low message rate. So any deltas that I have between simulation time versus hold time are going to be minimized when I compare it against other protocols that want to execute at wire speed. Operating at 1 hertz versus wire speed of 800 gig, it's it's radically different. So I listened to some of the presentations and I heard in our own words and mine that validation is hard. When you think about the simple-minded validation we're thinking when discussing with Ahmad is, okay, how do you know that PTP is working? Okay, you have the NIC PPS output. I can go and compare the output with one versus the other. I can put them on a scope and I can see what the jitter is. I can see what the offset is. But now you have a practical problem that you had to do that pairwise for 200,000 servers. So that's a very large number. And you have seen the diagrams from Facebook data centers. They are roughly the length of 2 football fields. So I need very long scope probes to be able to go to server 1 and to server N on the far side of the data center. So conceptually, that's a great idea. Practically, it's useless. Alon Regge from Keysight pointed out that ordinary clocks do not have self-monitoring means, and that's correctly stated. And he had a call to action, which was to standardize a monitoring method that will let us overcome that. And Matt has some ideas for that. And what I'm saying is, if I have a simulation model, come with your ideas. We'll tell you which idea is better than the other one for what the self-monitoring method should be. I have a few other examples. I want to bore you with that. The one that I think Ahmad was proposing is a subset of ordinary clocks compared with each other. If I want to compare across different GM and paths, I may have to have a server per GM that I may not have today. But if I have that, it enables client-side failover. I'd like to explore that in simulation. The current profile talks about grandmasters being single home. Maybe if I dual home, they might have path diversity. At the moment, it contradicts the profile, but I think it could be valuable. I saw a representation with a reverse PTP from Meinberg. Does it even work at scale? You may want to simulate that. The heat map coming from Ahmad is a great idea. What bothers me at the moment is that the grandmaster to ordinary clock uses a butterfly network, not a cloth, because it follows just half of the network, and you don't have as much path diversity as you have when you go ordinary clock to ordinary clock. So I'm not sure it's apples to apples. So I'm not saying that something is wrong or right or what the answer is. My suggestion is very simple. Validation through simulation could be a very powerful tool. So let's say that we convince OCP TAP that indeed simulation is the way to solve this problem. What workstream would you put us under? There are 2 possibilities. One is to create a simulation workstream. The other one that I think is even better is don't create a workstream, just attach simulations to the relevant workstreams. So we can go to the profiles that Michelle wrote, which today are a textual definition of what a profile is in the form of a document or part of a document, and I can give you a usable simulation model. So you say profile number 1, and by the way, here's the URL that gives you a model at scale for that profile. Have fun. The OpenTime server, the same. I can create a simulation model, so you can drag and drop that model or go to the topology builder and say, hey, I want a grandmaster according to OCP TAP. And of course, for TAP software, the idea would be to go from that monolithic synthetic representation of the workload and plug in whatever server you want in the software environment. These 3 ideas are much longer conversations. I don't want to go very far into that. I want to park them and go back to simulation models because first I have to convince you that simulations are worth pursuing. Any questions so far? Okay, a bunch of diagrams. So when we go to a platform and we say here is a model for an endpoint, namely a server, you see the NIC/adapter at the very bottom in green. You have the processor complex that may be an SMP or not SMP, a combination of cores and sockets connected to system DRAM, and there's a root complex and an endpoint. On the left, you see the partitioning to models that we simulate within the NS3 environment. We create a model for the network interface, and packet enqueue, the queue is the interface into that. Then you have data read and write in the form of messages from applications to a network stack. So when you think about model development, the granularity is what you see here on the left. There are models for applications, there are models for stacks, there are models for network interfaces. When I look at PTP, and this is based on the very nice PTP4L presentation from the Intel team, PTP4L will belong in the yellow box that you see on the left. And here I make again the case I made before that the beauty of PTP as a software layer is that it's actually separable from the application. The data plane that pushes lots of data goes over the thick red line, from application and network stack, but time is a service that the yellow box presents to application. And it's separable in the sense that I can prove correctness independent of the application that consumes it. And that is a very neat case where in most cases I don't have that convenience of the application being separable from correctness of the model. So if I were to do a model, yellow is what I would do for the software stack. The platform as it is today can be consumed two ways. There are model users, they don't have to code, they don't have to know NS3 or C++, they just write test cases using a GUI. It's a web-based interface, so if you have a laptop, which I'm assuming you have because you're watching this presentation, that's all you need. You get a URL, you open an account, there is an admin per company, and off you go. And you can start assembling networks out of existing components. In general, you can ask your partners, your vendors to share models with you so you can compose a network. But let's say that you're like me, you have no friends. Nobody wants to share a model with you. What do you do? So for every model that exists in the world, Scala has a generic model that we share with everybody. So we can have a NIC, you can have a switch, you can have a stack and everything else. You can get up and running. And that's until you start making friends. If you want to be a model developer, then you have to start using VS Code or the CLI or whatever mechanism you want. It's again remote. There is no need to buy any gear. Use your laptop and you can develop your model. And then after it's up and running, you can decide who to share it. You can just use it by replacing an existing model and do what if, or you can share it with the people you want to share it. The platform is, as I mentioned before, web remote access based. It's cloud hosted. It uses cold storage, so you never need to worry about deleting stuff that's in the disk, and it's pay as you go. What you get in the platform is a network simulation model at data center scale, a set of useful workloads and models were already developed, and there is an analytics engine that runs in parallel that, based on my guidance, for all the simulations I've run, so far I have not been proven wrong. The only thing I need to reason about is time. I never need to reason about throughput or buffer sizes or anything like that. When everything works. When something fails, you need to double click and say, oh, where is the bandwidth constraint? Where is the bottleneck NIC? Where is the buffer being exhausted? But when everything works, if it's a regression test, a pass versus fail can be done precisely on SLAs and time, reason by time, and PTP is an incredibly good example of that. Here's an example of the GUI that you get for the topology builder, where you get to choose what you're going to use for your spine, what type of workload. You can design heterogeneous racks and compose them into fabrics, into pods, and so on. So it's all GUI based. DC PTP is incredibly appealing as a workload because in a data center, it's likely to be the victim. So if you have very high bandwidth applications like ML training or flash storage or something like that, they move data at high throughput, but they may be stepping on other workloads. So whenever we do superposition, we always want to do superposition of aggressors and victims. And PTP could be a very sensitive victim, so you put it there as a way of making sure that there is enough capacity and enough traffic engineering that it doesn't get broken by other random applications. The other thing that's very unique, PTP has a remarkable ratio of precision to message rate. When we're doing, say, flash disaggregation, you're moving data at, say, 100 gigabit per second, that you're bursting very long reads. On the units of time that you deal with have to do with the jitter of the media or the protocol stack and so on. And they were in the order of microseconds to milliseconds, depending on the technology you use. And in order to do that, you had to do wire speed on 100 gig links. To have a workload that has a message rate of 1 hertz and the precision is 5 microseconds, it's incredible. It's just incredible. It's a beautiful workload to play with. But beyond ABC, and I want to bore you with seed, I want to speed up my presentation, but the main reason that we like the appeal of PTP as a workload is the impact of the work. Bad things really happen when distributed applications have the wrong time. And I have personal examples of in my personal life where I had to take a vacation and I bought my departing ticket to South America for Christmas and my return ticket for December 31st to do a 1 week in the sand trip, but I actually bought it for the following year. So that's a mistake that happens when you have the wrong time that cost me $4,000 to come back in the next plane. So I listened to some of the examples, especially on consistency of how bad things can get if you have the wrong time, if time goes back or stuff like that. So the impact that you can have is much more than what we have with other simulations that are by and large about capacity planning. Here, the impact is this is about correctness. So it has to be taken seriously. Looking at the state of the specs, things that I would say I'd love to ask and answer by running simulations, maybe it will take me after I have a model a week each, is do I really want to go hierarchical versus flat? When we started the conversation with Ahmad, we're thinking that hierarchical is the way to go just because a data center network is hierarchical. We do routing all the way to a rack switch, but from then on, it's a subnet and it's layer 2. And there is an architectural contract that says that the rack switch is the delineation between the network organization and the computer organization. That goes back to the enterprise days, that there are organizations that own the network versus the computer infrastructure. So maybe the rack switch is an administrative domain that we should preserve, and maybe we want a boundary clock there. So that I'd love to explore that. When you do that, we're going to explore the unique at scale versus the accuracy, because I'll have some boundary clock zero propagation. Keep in mind, we say no multicast, but we do have multicast at the rack. If we want to do a boundary clock that uses multicast there, or to use Amit Oren's proposal for the peer-to-peer transparent cloud to tackle scalability, that can be done. We could replicate sinks at the rack level. These are just thought exercises. I'm saying if I had a simulation, I would just spend a week on each. I'll give you the answers. The interactions between routing and PTP, I know we talked about them, but I have not seen a video yet that really goes in depth. Who kicks in first for failover? If my BGP kicks before PTP, or I'm relying on the failover mechanism of PTP. If both of them kick in, can it oscillate? Do I have one that can oscillate? Do I really need master failover, or I should be relying on client-side failover if I have enough grandmasters in the data center? I mentioned before that I'm not convinced that we really have path diversity when we're using half of the path, because ordinary clock to grandmaster is half of the network. It's 3 hops, it's not 5 in the typical representation. And I argue it depends on where the fault is and whether you're doing route summarization at the rack switches or not. What is the next hop that lags? Is a lag a single PTP port or multiple? Right? In the profiles, Michel says, I think the editor says that personally that the number of hops is constant. What happens during a routing loop? During a routing loop, you go around the merry-go-round and you have many more hops. Should we be doing something by putting a different TTL on PTP event messages so they are dropped and never go through more than one pass over a given switch? Should we create a notion of uplinks and downlinks? Because at the end of the day, a close is up-down routing, and you never want to reverse direction from down to up. So should we have configuration means that tell me what is an uplink and what is a downlink? So those are fascinating questions. Ahmad came up with a concern about ghost transparent clock scenarios. I think the concern is real. I've been on call many times, and I've seen many switches where the processor croaks, completely dies, and the switch keeps switching. Packets are being forwarded. So it's completely reasonable to assume that that processor misconfigured the device, intended to configure it for a transparent clock, but it's not, and the switch is forwarding packets. The only problem is you cannot guarantee that the packets being forwarded will have the residence time correction. So if I have a simulation model, I go explore, hey, can I solve this locally? If I have a switch model from a vendor and I can prove that I can do egress mirroring and ingress mirroring, and that the egress mirroring has the edited field, then I can mirror that to my processor, and the processor could be saying, hey, you didn't do a correction in this packet, you're misconfigured. If I don't have that functionality, maybe I have to do a heat map from all the ordinary clocks, comparing them across different GMs along the lines of what Ahmad was saying. But again, it's the type of questions that after I have a simulation, give me a week and I'll have results. Interactions between PTP and PFC, in particular POS. POS is a very handed way of solving congestion problems because you stop the entire switch downlink, and in general, you stop it asymmetrically in one direction. So what you essentially have is an asymmetrical speed link. So now the serialization delay is affected, and you can no longer assume that you have symmetry in your delay in the typical calculation T1, T2, T3, T4. So I would go model that. There was a talk by the time that he went into virtual endpoints. Virtual endpoints are a particular case of multi-host NICs. Any one of them is a pain. In the current proposal that I've seen from Dotan, the PHC is shared, but you cannot have many hosts disabling it because you have to do an active standby split brain election algorithm just to see who disciplines. If you do that, you violate the notion that the rack switch is the network service boundary, because one is creating a clock that is being used by the other servers. And whether the endpoints are virtual or physical, I think that violates isolation, because I can have one server attack the clock of another. I cannot assume that my neighbor is friendly to me. So that's a fascinating topic that if you have simulations, you can go tackle. What is protected capacity for PTP? Protected capacity in general is considered as what fraction of the links and switches can be down, that's a typo, on my SLA still works. But is PTP really based on an SLA? Can I rely on a P99.9? That's terrible if I have data corruption. Even AMAD postulating 5 nines is not very good for silent data corruption. It's good for availability, but not for data corruption. So we need to think about whether protected capacity for PTP is not at all about capacity. And the last one I have is a fascinating question of whether the PCI link is part of the network. The talk by Chris Hall from Intel was arguing that it is, and that PTM is the solution to that. So we extend our time error computation to the PCI bus, because he's right. The network is not over until the packets are in system memory. The fact that they're in the NIC is not that important. So the Scala models include PCIe, include a root complex model, so you can play with all that. But root complexes are not as interoperable or as public as Ethernet links. In general, there is no standards body that will tell you how a root complex behaves. They tend to be implementation artifacts of the processor that you pick. And in Chris' talk, he was mentioning one particular Atom processor, and he could not answer the question what happens with server class processors. The alternative, which I think was hinted by Dutan, is to actually alleviate the PCIe root complex issues by delegating time operations from the application to the NIC, because the NIC has the physical clock. And OCPTAP can run the simulations and pick a direction, say, what do we do? Do we measure time across PCIe all the way to application, or do we delegate operations to the NIC? So that's what I wanted to share with you. I meant to give some time for Q&A, like Ahmad asked me, and if there are no questions, I have one, which is, when do we meet in person? Let me stop sharing so I can take yours.
Great. Thank you, Ariel. Like always, again, this is the style Ariel presents, like leaves you with more questions. Okay, let's start with the audience. Any question?
So he mentioned something about a heat map. Does he have an example of that? Or?
I do. There are some public papers from Azure that were meant to find misbehaviors of network by creating a heat map of the rack to rack connectivity. So assume that you have agents in each rack, and they say, let's assume that every rack will ping every other rack in the data center. So they have a very elegant way of top-down representing the health of the data center by measuring the ping, the latency, and everything else. Along the same lines, Ahmad presented the idea that you, instead of having a ping, you do an ordinary clock delay request. So you take some ordinary clocks, they say randomly you pick some other guys. Would be great to have topological knowledge, so you know that you're going across people that are far away from you as much as you go to local, and you're going to people that rely on a different grandmaster than you. And then you can argue that you can paint a top-down picture of the data center that gives you an idea of the health of the clocks without having to instrument each one of the ordinary clocks.
Thank you.
Sure.
I think Lasse has also the same or similar implementation in TimeBeat. Lasse, do you want to add anything to that?
No, I'm okay. I mean, you know, I think that the hierarchical PGP model is fundamentally broken, right? And it cannot be fixed. Yeah, I agree. Let's say with the ordinary clocks speaking to ordinary clocks, right? That's essentially the solution. The solution is to stop believing in the determinism, right? And that's also why, as I'm watching this, I think to myself, yes, but all simulation is essentially based on determinism, right? And the problem is that I think it doesn't exist in this context. So yeah, those are my comments.
Yeah, say some more about the determinism concern to make sure I can address that.
Okay, I'm not sure I can add a lot of meat to the bone. You can only simulate something if you understand how it works, right?
That's correct. That's correct.
If there is no determinism, then there is no simulation. And my problem is that I think here determinism is hard to come by, is what I would say.
So let me tell you more about what we simulate, because I didn't spend any time on that. What we essentially have is queuing models for switches and for NICs. So when we do a tape out for a device, whether I'm Broadcom, Intel, Mellanox, whoever it is, you use discrete event simulators to simulate the RTL, and I've been doing that for all my life.
At a basic level, I understand that. Okay, but it is
awesome.
difficult to. But in the instance, okay, you also have to be able to predict. Okay, so you have a PTP client running on a particular server. It has a lucky packet filter, which means that it is very selective about what packets does it look at. What does it filter out before it passes something to its steering algorithm that ultimately adjusts the servo. And I don't think that if you do not know this, how can you simulate it? Do you see the problem? So with PTP4L, it's very easy. Okay, it's a stupid program, but not every bit of software is. So if you don't have the last piece of the puzzle there, I don't see how the simulation. Do you see what I mean?
So what I hear is that you're concerned about the endpoint lack of determinism more than the switches queuing model. Is that correct?
Let's say even if you can successfully simulate, for instance, buffer queues in switches and in NICs,
yes.
This is, let's say, only a fraction of the story, right?
That's correct. That's correct. And my point was that we start by having a synthetic representation of the endpoint, where we assume that we're going to accurately model anything that is networking, including all the network queues, all the schedulers in the NIC, the PFCs, and everything else. And we're going to idealize the compute, namely TCP state machines for the workloads work, assuming that they have infinite compute power. That is a great assumption for networking people because it exposes network bottlenecks in general. And then the next step is you make it more real by saying, I'm going to actually execute the real code of the stack. And we are in the middle of that journey.
Yeah.
So if I'm hearing right, here is like the concern is, like let's say the concern from your end is about the spontaneous behavior that, let's say, leads to something like lucky packet, which usually you say like simulation might have a hard time with it, because how would you again simulate these spontaneous events? Is that what you're mentioning?
Yes, I mean, it depends on what you're interested in simulating. But if your goal is to find out whether or not actually the clock on a particular endpoint is accurate or not, which I'm assuming, okay, is the goal of this particular simulation, yes, you would absolutely need to successfully simulate also this, right? Otherwise, how can you know? You want to simulate 200,000 nodes, okay. So in this case, if you are running time redundant, you need to also simulate 200,000 instances of, okay, what packets do we use to steer and to what extent and what algorithm and in what circumstance. And the logic around it is becoming awfully fuzzy, right? You know that. If you take PTP4L apart, okay, the logic is simple. More complicated application, it is not, right? And we do not have the hierarchical model where we take time from just the top of the rack switch or the next upstream boundary clock. We already look at other ordinary clocks and we carefully select this, right? And the basis of considerations about, okay, what was the variance across different connections in different time frames and so on. So it's very complicated, right? There's something. The problem is there's something chaotic about this, which makes simulation very difficult.
So I think that one thing that could be helpful is to watch the fidelity video we did with Keysight, because we're tackling exactly the same problem for TCP, not necessarily for time, but for TCP. And it's a hard problem because we're demanding that the TCP window opens exactly the same way across the simulated on the real life network that had a Linux stack and had cache effects and had a root complex, had DRAM and everything else. And what we did is to create a LAMP parameter model for a server on essentially fitting it by increasing the accuracy of that model until we brought it to within 1%. So just that might help you, give you a little bit of context on how we tackle that for the endpoints. Having said that, I'm not sure I'm familiar with what a lucky packet is. When you said that there is a lucky packet.
Well, it is essentially, so in PGP, okay, it refers to, suppose you have a source of time and a consumer of time.
Yep.
Okay, there's a minimum that it takes to send a packet from the source to the consumer and from the consumer to the source. Okay, it's a fixed minimum that cannot you cannot do it quicker than that. Okay, and lucky packet is a strategy where if you have packets that appear to transit in more time than that, okay, you disregard them. If you have packets where it appears that they left at a time and were received at a time which, if you subtract them from one another, gives a lower value than the minimum amount of time that you know that packets can transit in. Okay, you know that this can only happen because of a real offset between the clock and the source and the consumer. Okay, this is the principle of lucky packet. So essentially what it means is that when PGP packets are stuck in buffers, in network switches or network cards, okay, they're very easy to filter out. And in the software that let's say that I've written, that TimeBreed has, okay, we make substantial use of this, and it has increased, it has improved accuracy by at least 2 orders of magnitude, and in some cases more than that.
Okay. Any other questions on the presentation, on the idea of simulations and so on?
Yeah, I will take your word on. Let's make a work stream for it.
You like the idea of a work stream? Okay.
Yes, absolutely. Yeah.
Okay.
We'll do a work stream, and that's it. Like, while I understand your concern in general, like, I mean, when it comes to simulation, I mean, the sky's the limit. You can always simulate all the way down to atoms and quarks and whatever. So unrealistic. or like, I mean, as it comes with simulation, you always try to use some smart techniques. Like, you look at like an event. I know with chaos, even with chaos, I mean, you can always match a simulation model to have the same statistics as something real. And again, it's a simulation, and it will, to a large extent, it will give you, let's say, a good understanding of like what's going on. You can always inject more like perturbation in different nodes and so on. Like, I mean, it's I think the old argument of is simulation useful or not, and I'll say yes. Like, in most of these cases, definitely it can help. Like, does that make sense?
Yeah, and when we started the journey and we started applying the simulations to storage, we used to tackle that by using a phrase that somebody said, I forget the name, that said, all simulations are wrong, some simulations are useful.
Yeah.
That's the
it's
philosophy.
a model.
That you have to know what you're doing, of course.
I mean, physics in general is a simulation. Nature is a separate thing.
But for us, it's quite real, right? Because one of the things that we're interested in doing is find out, okay, how does TimeBreed work if you have a lot of nodes, okay? And so we take the approach that we must find a lot of nodes and run TimeBreed on them to find this out. So I accept that there's absolutely a place for this, right? And that in the real world, you can only get so far.
Understood.
And also, by the way, I'm also persuaded that I'm the idiot here, right? Because I think Ahmed is quite smart, and he seems to think you're quite smart, which leads me to believe that I'm probably the dumb one, right? But yeah, there we are.
Let's say you're very smart, and flattery will take you nowhere. Awesome. So let me thank you again for the time. I want to thank you for the time, for being here. We're more than open to come whenever you need us to discuss doing a work stream, doing contributions, tackling some of the problems. And if you're planning a face-to-face, getting the community face-to-face and showing up with more than one person.
Awesome. Okay, so no more questions?
Yeah, I guess
Okay.
maybe just one last comment, Ahmed, which is that I happen to know what time it is where you are, and the fact that you show up and you arrange this, okay, it shows tremendous dedication on your part, and I'm sure we're all extremely grateful. Right?
Thank you.
Thank you. Awesome. Okay. See you, everyone. Bye-bye.
Bye. Thanks.
Bye-bye. Thank you.